Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Manfred Paulini, who is a professor of physics at Carnegie Mellon University and a member of the CMS experiment operating at the Large Hadron Collider, the LHC, at CERN. He is looking for the production of dark matter particle in collision events at the LHC. He has also set up a lab at the university to build electronic devices for the upgrade of a component of the CMS detector called the NCAP calorimeter. In recent years, he has started to explore novel machine learning and AI-based approaches for event classification in particle physics, where he's interested to use ML to go beyond the classic data analysis approaches that have been used in particle physics for many years. Welcome, Manfred.
Good afternoon. Thank you for having me, Gil.
Absolutely, yeah. So I want to start with supersymmetry and really have a general discussion with you on what is supersymmetry and why is it important. My understanding, Manfred, and I have very, very limited understanding of this, is that we have a reasonably established idea called a standard model, but observations that we can't quite explain with the standard model. And so supersymmetry is a principle that might allow us to go beyond that. And I understand that there are multiple supersymmetry theories around. So do you want to sort of set the context for standard model first and why supersymmetry came about?
Yeah, let's do this. And I think you have a pretty good understanding. But maybe to sort of set the context, let's sort of define what we call the standard model of particle physics. And maybe we'll start with the atom, where we know, an atom is made out of, a nucleus that is surrounded by electrons. And then inside the nucleus, there are protons and neutrons. And now we know, the protons and neutrons have substructure, and there are quarks inside a proton and a neutron. And so these are, elementary particles that we consider nowadays as elementary. Inside a proton and a neutron, there are two different types of quarks. We call them up quarks and down quarks. And it turns out they sort of come in pairs, and we call it families. So there are sort of three types of families for a total of 6 quarks that we know nowadays. And yeah.
So just to, so we came a long way, Manfred. So we came from earth, water, fire as fundamental particles, to atoms, and then we got into quarks. So we know that now the protons and the neutrons inside an atom are made up of quarks, and there are a variety of quarks, right? How many different quarks exist?
There are 6 quarks that we know about right now. They're called up quark and down quarks. They have funny names, and one is called a strange quark and a charm quark. And then there's a bottom quark and a top quark, which is sort of the heaviest elementary particle that we know about right now.
And do they have they have a charge and a spin?
That's right. Yes, very good, Gill. Yes, so they have properties. They have a mass, which is something we do not understand very well, but they have a charge. And I alluded to there are, three quarks inside a proton, and we know a proton, has a charge of +1, electric charge. So the quarks inside the proton have like 1/3 of charge, and it actually turns out the up quark has a charge of 2/3, so of +2/3, which gives you 4/3, and then the down quark has -1/3, so this makes them +1 for the charge of the proton. So they have sort of fractional charges, and they also have spin. Yeah, yes, Gil.
Manfred. So one of the confusions I always get. So these 1/3 and 2/3 charges. Are they related to the charge of the electron, or something that we made up really?
No, they are really related to the charge of the electron. Okay. So as I sort of just try to point out, like, the proton is made out of 2 up quarks and 1 down quark, and each of the up quarks has a charge of +2/3. So this is, you add up +2/3 plus another 2/3 gives you 4/3, and then the charge of the down quark is -1/3, so this gives you then a total of 3/3 charge, which is +1, which is the electric charge of the proton.
Okay, and the neutron, the combination makes it neutral?
Exactly. So there is 1 up quark and 2 down quarks, and so +2/3 minus 2 times 1/3 gives you 0. It's pretty simple, actually, if you sort of think about it like that.
Yeah, it's very elegant, and so we have a handful of fundamental particles. It all sort of fits, but then we have observations that we can't quite explain, right? The standard model, is that the problem?
Yeah, so there are quite a few questions about the standard model, and some of them have to do with some of them have to do, for example, with the Higgs boson, which is sort of the last piece of the standard model that was discovered in 2012. And they have sort of, and they also have to do with sort of the forces that we sort of know about. So we just talked about electric charges. So there's the electric and magnetic force, the electromagnetic force. There's a weak force, which is sort of relevant for radioactive decays or for fusion processes in the sun. And then there's a strong force, which is important for holding the quarks with their charges together inside a proton in a very confined space. And then of course there is the gravitational force that we all feel as here on Earth. And these forces have sort of different strengths, and one issue is sort of the gravitational force is so much weaker than the other forces, which led to something that's called the hierarchy principle. And this is something that the standard model cannot really explain. So this is sort of one issue that's often pointed to, which is sort of missing in the standard model.
So I remember at the LHC, they found the Higgs boson. That was 2012, you mentioned?
Yeah, this was on July 4th in 2012. I remember very well because I had just been at CERN right before that, but then I had returned, and it was the 4th of July, where I joined a video conference at 3 a.m. in the morning here on the East Coast.
Yeah, I can't believe it's 8 years ago. Time is really flying here.
Yeah, it is true.
And so we needed the Higgs boson to sort of explain gravity, but the strong force that you mentioned inside a proton, now that force is not really mediated by another particle, is it?
Yeah, so the forces are all mediated sort of by mediator particles, and so the force, the strong force, is mediated by a particle that we call a gluon. So you can sort of really think of, the gluon glues together the quarks inside the proton. And, so we can we have sort of a model that also accommodates, the understanding of how these forces, interact with our particles, with the quarks, or then there's another part of the standard model, which is like the electrons. There are other particles like the electrons, and we call them leptons.
Yeah. And so you mentioned, so that this strong force inside the proton, it has to be really strong because you have charges in very close proximity there, right?
That's right. Yeah, that's right. Yes, yes.
And then you mentioned the weak force in the nuclear fusion, and so it all seems to fit, Manfred. So is the problem that we can explain the dark matter? Is that the first issue with the standard model?
So yeah, so this is one issue exactly that, we know from, cosmological observations that there has to be more matter in the universe, and especially surrounding galaxies or galaxy clusters, than what we can see. So the visible matter that is given through suns, and we know interstellar gas and all that cannot really account for some of the phenomena that we see. For example, the something that is called the rotation curves, how fast stars, for example, go in sort of the arms of, let's say, a spiral galaxy. They sort of go much faster than you would expect from only the visible mass that you see through all the stars inside the galaxy. And so that sort of led to assume that there has to be more matter in the universe, in the galaxies that we cannot see. And so this is where the term dark matter was coined.
And it's a pretty big chunk. It's about 25% of the universe, right? So it's not something you can ignore. But I know that there are some hypotheses around WIMPs and axions and other candidates that might make up the dark matter, and those things are not really are they part of the standard model, or how do those things fit with the standard model?
Right. So these are really not, so the dark matter that we know has to be there. We sort of really are very sure that this is not made out of standard model particles. So one, because it does not, it is sort of dark. So this means it does not interact through the electromagnetic interactions. So it does not, produce light or interact in a way that would produce light, which we then, would be able to see. And so, it could be something like, there are particles, they're called neutrinos. They are produced very abundantly in the sun, and they don't interact very much with, with matter. They go, through us, many of them, every second, and don't really interact. But we know from, the way the universe evolved that, for example, neutrinos would not be sufficient to explain the dark matter. So it has to be some kind of matter outside of the standard model. And so what you mentioned, like WIMPs, this is sort of weakly interacting massive particles. So it could be, some new particles that were produced, right after the Big Bang, but, are sort of left over since then, but they, only very weakly interact with our regular matter.
Okay. So neutrinos, though, are part of the standard model, right?
Correct. Yeah, that's right.
Okay. And so WIMPs, as you mentioned, weakly interacting massive particle, is really a hypothesis that is outside the standard model. So this would be something completely different.
That's right.
And are axions in the same sort of a way?
Yeah, so axioms are also sort of particles that are outside of the standard model. They come from some other aspects that have to do with sort of some of the flaws of the standard model. Let's see. So the WIMPs is sort of what connects us to the supersymmetry that we sort of talked about before. So supersymmetry is an extension of the standard model, and it has to do with what you mentioned before. The quarks, they do not only have charge, but they also have another property which we call spin. And so it turns out that the elementary particles, like the quarks or the leptons, like the electron, they have an half integer spin. Its spin is measured sort of in units of the Planck constant. And so we call particles that have a half integer spin, we call them fermions after, Enrico Fermi. But then it turns out that sort of the mediator, the force mediator particles, like the gluon or like the photon, for example, these particles all have an integer spin, so not half, but an integer spin. And so now supersymmetry is sort of something that sort of postulates that there should be particles, that sort of are symmetric, that sort of symmetrize this, that we have for each fermion, for each half integer spin, we have a partner that has, an integer spin of, instead of 1/2, but it has a 1. And for all the integer spin, force carrier particles, they are like half integer supersymmetric partners. So we sort of, double, with this theory, even more than double the, known particles.
And so how many particles are there in the standard model itself?
So in the standard model, we have, 6 quarks, 6 leptons, and then we have, the charge carrier. So we have the photon, the 2 heavy vector bosons, the W and the Z boson. We have the gluons, and then we have the Higgs boson. So this is, 16, 17, something like this.
16.
Yeah. So it's, yeah.
Yeah. Go ahead. Sorry.
No.
And so you mentioned, so the fermions have half a spin, the bosons have integer spins. And so the idea of supersymmetry is to take the standard model and essentially have a sort of a mirror reflection of that. So if you had 16, I don't know how many numbers are there. If you had 16 particles in standard model, you'll end up with 32 if you apply supersymmetry.
Yeah, so it depends a little bit on, so there's another issue with the supersymmetry. If it were like an exact symmetry, so for example, if we go back to the charge, charge is something that distinguishes particles from antiparticles. So for example, an electron has a charge of -1 electric charge, and it has also a partner, which is a positron, which is sort of its antiparticle. And the only difference between the electron and the positron is the charge, +1 versus a -1. The other properties like the mass, the spin is all the same. So if supersymmetry, were sort of the same kind of symmetry, you would expect that the supersymmetric particles would have exactly the same properties as our known standard model particles. In particular, they would have, the same mass. But we don't know, but we know that this is not the case because we would have, seen these kind of particles, even if they very weakly interact only with our standard model particles. So the symmetry, there's sort of a mechanism we call like a symmetry breaking. So it's sort of not an exact symmetry, but a broken symmetry. And so it depends a little bit how you do this breaking of the symmetry, which then gets into different models of supersymmetry. And you will then actually get more than, double the number of standard model particles. You will actually quite get a few more. And there's also, then sort of interactions, how they interact with each other. So you get, quite a bit more free parameters in this model.
But is the dominant one spin, Manfred? The way that we kind of reflect these particles is predominantly spin?
Right. So the only difference between, our standard model particles and the supersymmetric particles would be the spin plus, the mass. So we sort of think, the masses are sort of in a range where we could produce these particles with a collider like the Large Hadron Collider.
Yeah, so I want to talk about that. So you're spending a lot of time in the LHC. For many years, these experiments have been going on. I understand, Manfred, that looking for the supersymmetric particles, but so far we haven't found them, right?
That's right. We have not found any. And, there's people who sort of think, well, we have looked for these supersymmetric particles for, 10 years, 20 years. There were already searches, not only at the Large Hadron Collider, but at, colliders before that. And there people say, well, it looks like these supersymmetry, these particles don't exist. Now, as I sort of try to allude, is that, we don't know exactly how this supersymmetric theory really works. We don't know exactly what the masses of these particles would be, how they will really, predominantly produced. And what we have been doing so far is sort of look for very sort of reduced and scaled down versions of, maybe a full supersymmetric model in order to sort of be able to, to search for something that is sort of easy to look for. And we have sort of realized, well, sort of the low-hanging fruits in supersymmetry, it doesn't look like, there's a lot of low-hanging fruit there. So we have to sort of get a little bit more advanced and maybe think a little bit and maybe consider other ways, these supersymmetric particles could be produced, or look in different phase spaces. So it's not like, we haven't found it yet and we should give up. I think there is, quite a bit of enthusiasm still to, continue to search for supersymmetric particles at the Large Hadron Collider.
Yeah, it's sort of an asymmetric experiment, right? If you find it, then it gives good credence to supersymmetry. But if you don't find it, you cannot reject it. Right?
That's right. Yes, that's right. Yeah. So this is, this is sort of the interesting thing about doing research. You don't really know what you're looking for, and there's always, a back and forth with, theoretical models and, people who come up with great theories. And then there are experimentalists like me who sort of search for them. And if we don't find them, then, this is sort of feedback for people who build other theoretical models. And the really exciting thing is, you don't know what nature really has in store. Supersymmetry is, mathematical, a very, elegant theory, but it is very possible that, nature hasn't really realized this and has maybe realized something completely different that we don't think about yet. And so this is sort of this back and forth between, carrying out an experiment and verifying a theory, like, we have verified our standard model for many years, versus, looking for a theory that's not yet proven. And, as I said, nature might not have realized this kind of theory, even though, to us it appears mathematically very, elegant.
You mentioned the CMS detector that that you are making at the CMU. What exactly is CMS?
So CMS stands for the compact muon solenoid. So it sort of describes a little bit sort of some of the elements of the detector. So the detector itself is, a large. It's sort of large like a house. It's really big. I sometimes like to sort of tell the story that some years ago, maybe 5 years ago or something like this, I spent the summer with my family at CERN. And it was in a time like now where the accelerator didn't run. And so we were actually able to go down in the cavern and, look at the CMS detector. And I had told, my wife and my daughters, they were, I don't know, 13, 14 at that time. Yeah. It's really large, and so we come down there and, the first thing they say, wow, it's really large. Like, like who listens to that here?
No. So I don't know. People say LHC is the sort of the largest machine that we ever built, right?
Yeah, I think this is really correct. I don't want to sort of get into, we are larger than others or into the, bigger is better aspect. It is, so the collider, it is in a tunnel that is about 100 meter underground in the Geneva area in Switzerland. And the tunnel itself has a circumference of almost 17 miles. So it is really, quite a big instrument. And then, the detectors themselves, just maybe to give a few numbers. So the CMS detector is about 15 meters high, 15 meters wide, and about 20 meters sort of long, sort of really like, a house. And it's made out of different components. And it's called compact because it has a lot of like steel in its outer like more even than what it's in the Eiffel Tower. And I sometimes try to point out it's also called compact because there's another experiment, a sister experiment, which is called the Atlas experiment. And it is twice as large, like twice as long and twice as high. So that's why we are sort of compact.
So there are two ways to potentially improve the sensitivity, right? One is to increase the energy level, and the other is to increase the sensitivity of the detectors themselves. I guess the energy can you go much further into increasing the energy levels?
So with the LHC, we are sort of have almost reached its design energy. So when the LHC started, it sort of started at half of the sort of design energy, which is 14 giga electron volts. We sort of talk about energy in these electron volts, which is sort of an energy that a charge sort of would accumulate it if it goes through a potential of like, of 1 volt difference. And so it comes in like, mega and giga, sort of what we know from our computers. And so the LHC is, 14 tera electron volts. And we have operated it at 13 so far. So there is not very much room. We're sort of, at the sort of, at its top energy. The exciting thing that is coming in about 5-6 years is the collider will sort of go into a mode where they increase the rate of collisions with which we sort of collide the protons. And this is another way to sort of increase the sensitivity by sort of, increasing the number of collisions and sort of increasing our data rate, by at least another factor of 10.
So that's a big difference. And the detectors, and that is where engineering could continue to improve the sensitivity of the detectors, right, over time.
That's right, yes. And, sometimes, like when we go into this, we call it the, high luminosity phase. Luminosity is sort of a quantity we use to sort of express the collision rate. So when we go into a high collision rate phase, we produce so many particles, in these collisions that the particles that go through our detector, they sort of act like radiation towards, our detector devices, and they sort of damage them. And some of them, they do not really function at that time anymore. And so we, replace them with actually new technology. And this is, what we are involved here in at Carnegie Mellon, where we sort of, have set up a laboratory to build some new devices for our upgraded detector.
And so after having been involved in this for a long time, Manfred, where do you come out right now in terms of the credibility for the supersymmetry principle after having looked at all the data?
Yeah, where do I come out? That's a good sort of question. As I sort of, mentioned earlier, I'm still, very excited about continuing to search for supersymmetry. But, clearly at some point, if we really do not find supersymmetry, we will have to sort of declare that, if supersymmetry exists, it does not exist at energies or masses of supersymmetric particles that we can, reach with the Large Hadron Collider. And again, it could certainly be that these particles have masses that are sort of just beyond, the reach of the current collider. We don't know, that's exciting, of course, too.
Yeah, I always think that God has a sense of humor,
Right. Yep.
You're teased with some bits, but you can't really get it.
That's right. Yeah. And I always sort of think, nature will always, tease us with something new and keep us searching and searching. I don't think we will ever completely understand, the whole universe. Even so, the dream of physics is really sort of to come up with this, theory of everything. But I sort of, so far we always, kept going, and there was always where sort of physics felt like, oh, I think we understand everything. Then a completely new door opened, like, more than 100 years ago. Quantum mechanics opened a completely new, area of physics that nobody sort of thought about. And we have sort of just to, keep searching to find this door that gives us this glimpse into, this new world of understanding.
Right. We'll take a quick break, Manfred, and when we come back, we'll talk about some of the machine learning approaches that you're applying to particle physics.
That would be great.
Thank you. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. Manfred, we were talking about supersymmetry as an extension of standard model, which then requires, not necessarily require, but then hypothesize a variety of particles that we haven't seen. And one of the objectives of the Large Hadron Collider in Geneva is to see if we can actually detect some of those particles in major collisions. Major experiments, and so far we haven't found them. But more recently, you have been applying this emerging ideas in deep learning and machine learning in particle physics. You have a paper out entitled End-to-End Physics Event Classification with CMS open data, applying image-based deep learning to detector data for the direct classification of collision events at the LHC. This seems great application because you have tons and tons of data, and I wonder. So this will be more in unsupervised learning, right? Because you don't really have labeled data in any way, do you?
We do. I mean, this can be in supervised learning, unsupervised learning. So maybe sort of just to connect to what we talked about before. We talked about upgrading our detector, making it giving it sort of better hardware, better instruments. So this is sort of one way to sort of improve your experiment, and the other is to sort of become more creative with respect to how you analyze the data, how you try to tease out certain effects, and or how you try to understand the data. And machine learning is a very, very popular way sort of to do this. And I have to admit, I have ignored machine learning for quite a long time, which I always sort of said, look, what is this machine learning all about? We here in particle physics, we have been using neural networks for like 30 years to, classify our data. What are you guys sort of talking about with this machine learning, And I've really sort of ignored it. And like 3 or 4 years ago, one of my graduate students sort of became a little bit interested in machine learning. And, this is a great thing, and the beauty of being a professor, you learn with your students, and often you learn, from your students. And we sort of, started to talk, and I sort of realized, there's quite a few things that I had ignored, that I had not paid attention, that happened, beyond sort of the neural networks or boosted decision trees or multivariate type of analysis approaches that, some people also call machine learning, but there's quite a bit more that I had sort of really ignored and not paid attention. And these things, have to do with, images and, how images are recognized, and how you work with images. And, this is all driven by, image recognition, face recognition, where, a lot of advances have been made, as well as, the autonomous driving, all the, driverless cars that, process images, very, very quickly. And, I had really not realized, wow, there's quite a bit out there that I had not paid attention to. And so, then, my student and I really got into this.
Yeah. And, it's one thing that has happened, as you know, last 10 years is that the computing capabilities have gone up significantly, both in terms of CPU power as well as memory. So you can take and hold very large amounts of data and memory to do some of these things which we couldn't before. Mathematics itself, like you said, neural nets have been around from the 60s. Many of the machine learning techniques have been around. Both engineering and physics have been using them. And so it's not really advancement in mathematics, but more advancement in technology
Yeah.
that might allow us to do some of these things. But I want to dig a little deeper into this, Manfred. So do we have so let's say we go in and we're looking for a specific particle. And from the experimental design, do we have an ex-ante expectation of what that image would look like?
So maybe let me explain a little bit how we sort of do like a data analysis. So how we sort of analyze the data that are taken with an experiment like the CMS detector. And then I can sort of relate it a little bit, what the ideas that, that I have sort of worked on in the past few years with respect to using sort of machine learning for that. And they are sort of somewhat connected, and we will sort of get to your question. So when the Large Hadron Collider, collides like protons and, energy is transformed into some matter, new particles are created, and so the only particles that we can really see are particles that live long enough that they can go through our large detector and interact sort of with the matter there. And the way they interact is often, in form of, like we measure some charges or we measure some, some electrical signals. So sort of what we call sort of the raw data is sort of in principle some, electrical signals in the detector. And we sort of record this. But then we want to sort of relate this to really something that happens, in the initial collision. So we want to really like translate this into the particles that were created. And so
Quick question, Manfred. So these are proton to proton collisions that we are talking about?
Yes, this is the LHC collides two protons. So what actually interacts is sort of the constituents inside the protons. So there is, like we talked about, the quarks and the gluons that are inside the protons. And if we sort of look what sort of the most interaction rate or the highest rate is sort of the gluons from one proton would sort of interact with the gluon from another proton, and sort of their energies that we give these protons then create sort of new particles. We call this like new pairs of particles sort of coupled to these gluons, or they could also new pairs of particles can be produced. And a lot of these particles, they decay very quickly into more particles, and then, with some energy, other pairs of particles are produced and so on. And so this sort of results into often a large amount of hundreds of particles to be produced in these proton-proton collisions.
So I know that you take these protons, they go around the tunnel many times. So by the time they collide, are they getting closer to the speed of light, or what is the speed at which they collide?
So when the protons go around in the tunnel, they go more or less with the speed of light. It's sort of like 99 point, and then there's like 10⁹% of the speed of light. So it's really like the speed of light. And so they go around like 11,000 times per second in the LHC tunnel. So in the 17 miles ring, they run around there like 11,000 times per second. And I often sort of talk about the LHC is beyond underneath one part is underneath a French part, and the other is underneath a Swiss territory. So they cross the border like 11,000 times a second.
Right. Passports are out of the question.
Yep, exactly. These are, I guess, the open borders.
And so when they collide, as you say, gluons might interact. They might create new particles. They might decay into other particles. And so the trick here is to have very, very sensitive detectors and really capture all the data that then could be analyzed at a later time.
That's right. Yeah. So we have sort of different sort of sub-detectors. One sub-detector sort of gives us, points in space where sort of particles, charged particles go by. Other detectors measure like the total energy of, a particle like an electron that goes into this device, or other particles only interact with some chambers that are sort of on the outside of the CMS detectors. And so we sort of use this knowledge like, if you have three-dimensional space points, you sort of need to connect the dots in order to sort of get the trajectory or the path of particles. And so this is sort of something that we call the, where we process the data. So where we sort of turn the original electric signals into something that is related to really, particles are being created. And there are sort of other methods where you then can sort of assign, a track or a trajectory to come from a certain particle, and then its momentum or its energy. And so in this data processing, we sort of create certain what we call objects. We have that then relate to certain particles. So we have, for example, an electron object that would relate to a particle that went through, so it was very likely an electron that went through our detector. And so in the end, we have sort of, for every event, we have sort of big tables of these kind of objects, electrons or, protons, for example, or, there's bundles of particles that we call jets and so on.
These are, if I understand it correctly, Manfred, these are things that you're not interested in. So are you trying to sort of subtract out?
So this is sort of the regular way we sort of do our analysis. We take the raw data, we sort of reconstruct the data, and so we put sort of information into this reconstruction process, and then we sort of have these objects, and we sort of put sort of some intuitive knowledge into this. And then often, in order to search for a new particle, you would work with these objects and maybe sort of feed them in some, classifier or something like this. And so when my student and I sort of really sort of got into, machine learning, the first thing we wanted to do was sort of really sort of start with the raw data in order to understand a little bit what the machines can really do. And my idea was always to sort of really try to sort of go beyond what we can do with, regular techniques. This is something new, it's very fancy. Let's see whether we can use it to do better than, the standard, so to speak. And so I always like to start with sort of simple projects. So we started with a very simple project that was related with the detector component that my group is involved in, where we have some, responsibility, operating this detector component, and it's called the Electromagnetic Calorimeter. And I don't want to go too much into, what it does, yes, so that we can maybe focus a little bit more on what I actually wanted to do. And so we did a little project where we wanted to sort of distinguish, whether one can distinguish an electron or a photon being, measured with this electromagnetic calorimeter. And with regular means, you cannot distinguish this. But we sort of really used so the first thing, we needed to sort of turn our data into sort of images, which for this electromagnetic calorimeter was sort of easy to do. You can sort of give different colors to sort of the energies of what we sort of measure. And it sort of turned out, that, that we actually, using machine learning, we could actually distinguish, an electron from a photon, which was, very, very something that you could really not sort of do before. And this then sort of got us to the idea of, what about, we sort of just take the raw data, give it to a machine, and then sort of ask the question, do these data contain a new particle, or do they decay? Do they contain, the decay of a Higgs boson, for example? And sort of like forget about all the, reconstructing the data, forming these objects, and then doing something with this. And so this sort of got us into what we call this end-to-end approach of data classification. Sorry, Gil, this was a little bit a long story. You probably have some questions that you had along the way.
Yeah, that makes a lot of sense. So simplistically then, if we can look at what could happen to known particles like electrons and photons, you could then use that as labeled information in the image, right? And so if you are from the experiment, you're finding an image that, correct me if I'm wrong, Manfred, if you're finding something that has low probability of fitting with anything that we know, then maybe that is data that requires further analysis. Is that it could be used as sort of a filtering out things that might not be that interesting?
Yes, very good, Gil. Yeah, so you sort of have the right idea. So one can then, of course, sort of think further. One can sort of, and this is sort of still very hypothetical, but because it would really require understanding all the detector responses very well, and also understanding a lot of reactions that happen in our detector that come from the standard model particles. But one could sort of imagine that we tell the machine sort of, look, this is sort of how events from our standard model all would look like, and now these are the data that we took with our detector. Go and find some anomalies, and this is again something that machine learning can do very well, which is called anomaly detection.
Right.
And this is sort of an idea that not only I had, of course other people do, and trying to sort of use machine learning is sort of trying to go into this direction that the machines would sort of tell us, hey, this is sort of a really anomalous looking event.
Yeah. That makes a lot of sense. So, so this is not something that we have been doing in LHC type experiments yet. We do more conventional statistical analysis.
We have been doing a lot of conventional statistical analysis, but we have been also now started to really do and use more sort of machine learning based techniques. If I maybe sort of can give another sort of example of what we're trying to do with sort of anomaly detection. So one task that my group has is to sort of monitor the data quality of this subdetector, this electromagnetic calorimeter, while we take data. You want to make sure that when we take data with our detector and record this, that everything functions. And so we have, so my group is sort of responsible for like a software package that sort of really looks whether there is, some power supply not working, and so a little part of the detector might not be functioning, or there's maybe some part of the detector that fires every time there's a collision, which of course you don't want. And so there's sort of like, very regular software that sort of checks for all this. And you always have sort of, task rules that you have to sort of code. But another way to do it is, to use sort of machine learning, and you sort of can show the machine like, this is how, when the detector functions, how things would sort of look like, and then leave it to, an anomaly detection code, or, when you run this, that sort of would flag for you sort of, oh, there's something that does not look right. And so this is something we want to sort of implement for the next run of the LHC. So things are, we're really starting to use, machine learning.
Yeah. So in conclusion, Manfred, I want to ask you how you think this area would develop in the next 5-10 years. So I can speculate that if these techniques are improving, one could imagine sort of continuous experiments being run and managed by machines. And if anomaly detection is robust enough, you could potentially remove a lot of humans from the process. And when there's a high confidence of an anomaly, then that is only a small subset of the data. that requires further analysis. In other words, do you see this going to more of an autonomous experiment type process in the future?
Yeah, certainly. Because one of the things that we also have to do is, we cannot record every collision. We cannot record what happens in every collision. So we always have to sort of choose which collisions we record and sort of, write on tape. I mean, nowadays you don't write on tape, of course, anymore. And certainly, machine learning is something that, will play a big role into sort of more autonomously make these kind of decisions of what data are sort of recorded. But I also sort of want to, make clear it's really, the humans are still the ones who sort of can devise these kind of things.
Yeah.
It's really, and I see this, when working with my students, you cannot sort of just, let some algorithm loose onto some data sets. You have to understand what you're doing, and you have to sort of have the intuition and the knowledge of like a scientist or a physicist to sort of really understand whether this is going in the right direction, whether this is producing results that really make sense. So, it is still, it is, for me, machine learning is sort of a tool, that we use, like we have used, computers as tools in the past. So these are, fancier tools, but it's really up to us, the humans, to sort of use these tools in the right and in a wise way.
Yeah. In my thinking on that, Manfred, is that in particle physics experiments, maybe machine learning is a way to discard data that will make humans more effective in finding what they're looking for. Because one of the issues that we have in other domains is that it's not lack of data,
right?
It's just explosion of data. And so if machines can remove most of the noise, and then focus the humans on a very small subset of the information that may have some utility, then that is very useful.
Yes, Gill, this is exactly, you see it quite correctly. This is also sort of the way I see it, that, these are tools that really can help, discard maybe a lot of data that are not of interest. And so we can sort of focus on what's of interest. And this is exactly what also, machine learning is doing in other domains.
Yeah. In conclusion, Manfred, do you see that LHC will continue on the supersymmetry track for at least in the short term?
Yeah. Yes, certainly. Yes. I mean, we will continue to search for supersymmetry or for other, physics phenomena beyond our standard model. This is certainly, something that the LHC will continue to do. And as I said, in 5-6 years, there's a new phase that is happening, and the LHC will continue to run for, at least 10 years beyond that, until probably 2035. So it's certainly an ongoing experiment. As I said, if we do not find supersymmetry, then we do have to, go somewhat back to the drawing board and try to sort of see what else could be going on. And there are other things that, of course, are important, like, studying the Higgs boson and studying its properties, and, like producing 2 Higgs bosons that, give us an idea about, the Higgs field, and maybe let us understand this mass mechanism better. So there's quite a bit that, a large, device like the Large Hadron Collider can help us to understand about nature.
Yeah. I know that, Manfred, Japan had some plans to create a more energetic collider.
Mm-hmm.
Status on that? Is it still?
Yeah, so Japan has been talking about to sort of take the lead to build what is called a linear collider. So there, electrons and positrons would be collided. And the reason, one issue is if you put charged particles into like a circular orbit, they radiate radiation, and so they and the lighter the particles are, the more they sort of radiate. So if you want to accelerate particles like electrons to very high energies, you would have to put them on a very, very large sort of orbit so that they don't go sort of around the bend very radically. And so the easiest to do it is, do not have them in a circular collider, but in a linear collider, in a straight collider. And so this is sort of a different type of accelerator that has been talked about, and there have been plans to do this in Japan for quite some time. But, these instruments have become, very large, and they cost a lot. And so, there's often, international agreements that have to be made. Like, the US contributes to the Large Hadron Collider, which is, in Europe. And, this sort of then brings us into, government funding and, budgets and these kind of discussions. I don't know how far we want to go into this, Gill.
Yeah, there's a lot of uncertainty there as governments change and as ideas change. The linear accelerator, so that has to be really long, right, for it to work?
That's right, because, you have to sort of accelerate the electrons from like 0 to very high energies. And the way this is sort of done is in sort of like cavities, which is sort of electric fields that sort of, that give a boost to these electrons or charged particles. And so you sort of have to stagger them, and it sort of, this will be like mile-long accelerators. And they would sort of operate in order to, for example, produce a lot of Higgs bosons, so that you can, for example, study the properties of the Higgs boson very well, which is something that is, very interesting to do.
Yeah. Excellent. Yeah, this has been great, Manfred. Thanks so much for spending time with me.
Yeah, thank you very much for having me. I really enjoyed this. Thank you.
Yeah, and good luck with this research. Thank you.
Thanks.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.